Okay, good afternoon, everyone. Welcome back to College Algebra. This is Professor Win. So we continue with the second part of the lecture last time. Um, so based on the division algorithm, the long division and the syntactic division concept, today we want to talk about the most two important theorem in college algebra. This theorem were discovered by a mathematician named Bezout. Okay, Bezout. Okay, the first theorem I want to talk about, okay, is remainder theorem. Okay, remainder theorem was discovered by this guy. I think he's a French mathematician. Okay, and the remainder theorem is very important. You know, I think I consider it as a tool to find the output with the given input of the function. What I mean also over here is that, when back in the day when you learn function, right? You learn how to evaluate function at certain x value. You replace the x with the new x value. For example, like if you want to evaluate a function at x equal 2, right? You plug 2 into the function. Okay, so the remainder theorem is does not only help you to find a remainder when you do syntactic division or long division. It helps you to find the output given the input. So instead of evaluate it in the same way as you already learned, we can use the remainder theorem to evaluate a function at certain x value. Okay, for example, the example last time. Okay, let's consider the example last time. Last time when I talk about syntactic division, okay, I give you example like this, right? And this is the dividend, right? This is the quotient, okay? This is the quotient, and we just take the c value to set up the syntactic division, right? And I take all the leading coefficient here to set up the syntactic division. And when I do after I finish the syntactic division, I know the 17 is the remainder. Okay, so I know that when you do syntactic division, you can find the remainder. Okay, but the remainder theorem also give you this information. Let me rewrite the syntactic division last time. Okay, so I take 4, 0, negative 28, negative 7 as to set up, right? Then I drop down number 4. Okay, so I have 12 here, and I multiply this, give 12, add them up, right? This is give you 36, add them up. Okay, add them up. Okay, and this is give you 24, add them up, give you 17. So this is a remainder. Okay, and the question is the function p of x for x cubed minus 28x minus 7, and the divisor function is x minus 3. What 17 means over here? Well, we all know that it is the remainder, but based on the remainder theorem, Bezout say that when you plug 3 into the function p of x, when you plug 3 into the function 3 of x, okay, the output is 17. That's what Bezout say. Okay, that's what Bezout say. And when he extrapolated based on a lot of maybe his a lot of syntactic division, when he do a lot of division, yeah, he extrapolated. That's why he can come up with the remainder theorem. I'm going to talk about remainder theorem later. But let's check that's what he say is correct or not. Okay, so let me see. I plug 3 in here. So P3, we evaluate function P at 3. Okay, let's say it gives you 17 or not. So give you 4, right? You plug it in here, 3 to the third power, negative 28 times 3 minus 7, right? And, oh, I think, where's my calculator? Sorry. Okay, let's see. Let's see my output. Let's see our output is 17 as digit C or not. Okay, so this is give you 27, right? 27 times 4. 27 times 4 give you 108. 28 times 3 give you 84 minus 7. So 108 minus 84 minus 7. Oh yeah. Oh my God, look at that. It really give you 17. Oh, so you see the Bishop is right. He say that when you plug the C value into the P function, the polynomial, the dividend, this is the dividend. The remainder is actually the output of 3. Wow. Of course, there's a way to prove it, but I'm not going to go through the proof. So based on this answer, Bishop come up with a theorem. It's called Remainder Theorem. And the Remainder Theorem states this. If a polynomial, okay, so this is the Remainder Theorem. If a polynomial, Px, okay, this the dividend, okay, is divided by x minus c. So x minus c, you know, when you divide by x minus c, c is the value. C is the input of the p of x. That's what I mean. Okay. Then p of c is equal to remainder. Wow. Wow, it's equal to remainder. Okay. That's what the remainder theorem said. Okay. So I'm gonna box it. So this is the remainder theorem. Okay. Then what happens if the remainder is 0? Okay, put remark. If the remainder is 0, after the syntactic division, after we finish syntactic division, the remainder is 0. It means that over here is 0. Okay. Then based on the remainder theorem, we have P of C equals 0, right? Okay. And if P of C equal to 0, what is that? What is that? What is that? You remember when we learned a polynomial function, okay? After you plug the value into the function and it turned out to be 0, we have a name for that, right? I don't know if you guys remember that or not. If you plug into the function and it turned out to be 0, okay? There are two names. Okay, before when you the first few weeks of this course, we call that x-intercept. Remember when you plug a value in and it turned out to be 0, it's called x-intercept. And so back in the day when you find x-intercept, you know, you set the function equal to 0 and you solve for x, right? But later we have another name. We call it 0. So in this case, c is 0 of equation P of x equals 0. So C is actually 0. So I'm gonna say C is the x-intercept value. Or geometrically, the graph of a polynomial function, okay, the x-axis of the coordinate system, okay, is intersect the graph of polynomial function at x value equals c. That's what it means geometrically. Okay. All right. Let's do another example. So this example I used to demonstrate to deduce the remainder theorem discovered by Bézout. Okay, all right. Let's do another example. Example 2. I give you the function polynomial like this: p of x, x to the 4 plus x to the 3rd. Okay, minus 6x squared. Okay, minus 5x minus 15. And I say that use remainder theorem to evaluate f of phi. Okay. Okay. So without learning remainder theorem, this is what you do. In order to evaluate f of phi, you plug phi into the function. That's what you use to learn, right? But because I asked you to use remainder theorem, so you have to use remainder theorem. Okay. So how we do that? Okay. It's easy. So phi in this case is c. C equal phi. So we just need to set up the syntactic division if our remainder is turn out to be a number, that number must be the output of f of phi. Of phi. I'm sorry. Okay. So I set up the division. For phi here, I take the coefficient of this polynomial. So 1, 1, negative 6, negative 5, negative 15. Okay. So I drop 1 down. So 1, 5, 6, 30. Give you 24. 5 times 24 give you 120. 5, add them up, give you 115, right? 5 times 115 give you 575. And you add them up, give you 565. So the last value here is the remainder. The remainder. It means that based on the remainder theorem, f of phi, or in this case, it's p of phi. I'm sorry, it's evaluate p of phi. It's not f, because I name it p over here. So p of phi must be 565. And here you go with that. Oh, so you see that remainder theorem is very important. It is very important. It is the tool to evaluate the input, okay, of the function. In this case, it's the p of x function. Okay. All right. Another theorem I want to talk about in this lecture video, it is called factor theorem. Factor theorem. I need another piece of paper. Let me see, where is that? Oh, right here. Okay. The factor theorem is this. It was discovered. It's not discovered by Bézout. Okay. At the beginning, I thought it was discovered by Gauss, but it was not either. I looked it up on internet, and there's no information about a factor theorem. I know that factor theorem is actually is deduced from the remainder theorem. So if you guys have a chance, you guys look it up on internet, and you guys gonna help us choose to know like who discover what mathematician discovered this theorem for me. Okay, I try to look it up, but I don't see any information about that. Okay, but I know the factor theorem was deduced from remainder theorem. Why I say that? Because just think about it like this. We learned division algorithm already, right? And the division algorithm state that f of x equal to d of x. D of x is the divisor, times q of x is the quotient. Okay, this is dividend. Okay, this is so we have learned Okay, this is quotient. This is the divisor. Add to the remainder of x. So you see that if I set r of x equal to 0, if I set r of x equal to 0, it means the remainder equal to 0, then my function become what? My function become f of x equal to d of x times q of x, right? Then in this case, you will see that d of x is actually a factor of f of x. You know, when I stopped over here, some student was like, "Okay, what's factor? What factor is? You know, you guys forget what factor is. You guys remember when you first time sixth grade, you learn how to find factor of number. Okay, so this is recall. Okay, so you know that 6 equal 2 times 3, right? 6 equal 2 times 3. Then I know that 2 is a factor of 6, right? The reason 2 is factor of 6 because 2 go into 6 evenly. So f of x equal to d of x times q of x. So d of x is a factor of f of x. Or q of x is also the factor of f of x because d of x and q of x, both of this, okay, goes into f of x evenly. That's what I mean. That's the definition of factor, okay? Okay, so in this way we know 2 is a factor of 6 because 2 go into 6 evenly. And similarly, d of x is a factor of f of x. Okay, now we want to take p of x, okay, and we want to divide it by x minus c, right? Okay, by x minus c. Then based on division algorithm, I can write this. I can write p of x equal to x minus c times quotient, right? We don't know what quotient is. You know, when you take a p of x and you divide by x minus c, it gives you the quotient, okay, and it gives you the remainder, okay. And the remainder could be a number, could be the expression with x, could be the function like this. But if rx equal to 0, okay, if I have x equal to 0, same thing as this, okay, then p of x become x minus c times q of x, right? Right? So you use the concept we already learned in sixth grade. That x minus c is actually a factor of p of x. Oh, wow! Look at that, guys. We just suddenly discover a new theorem, the theorem we call factor theorem. So the factor theorem states this: if, okay, if x minus c is a factor of p of x, okay, okay, then this is equivalent to, okay, f of c equal to 0. Okay, so I want you to box this. This is factor theorem right here. Okay. Let me explain to you what does it mean here in detail. If x minus c is a factor of p of x, just think about it. If x minus c is a factor of p of x, it means that the remainder is 0. Okay? And the remainder is 0. It means that f of that value equal to 0, right? Well, we already do the problem here, right? If p is c equal to 0, okay, then c is 0, 0 of the p of x. Okay, or it means P of C, C is a 0 of P of X. This is the same as P of C equals 0, right? Same thing. Same thing. This all the statement here are the same. So over here we know that X of C is the factor of P of X. Then F of C must be equal 0. Remainder, because 0 in this case is the remainder. Okay. So how I'm going to use factor theorem to do the problem? Let's go to example. It's very simple, guys. You know, it's kind of sound very complicated, but when you do the practice, it's very simple. Okay. How we do this? Okay. Let's see. Okay. So I give you a function f(x) is 3x to the third power okay, plus 25x squared, okay, plus 42x, okay, that's 42x, minus 40, okay, and I also say that negative 5 is a 0 of fx. So the first question, I want to factor, okay, f of x. And the second question is, I want to solve the equation. So equation 3x to the third plus 25x squared plus 42x minus 40 equals 0. All right, so there are two parts. So we're going to do the first part first, okay? Solution. Okay. I want to factor f of x. You know, the factor form, it means the product form. Okay, it means that you have to put in product form. Same thing, you factor the number 6 is 2 times 3, so it's the product form. Okay. What do we know? We know that negative 5 is 0 of f of x. And if negative 5 is 0 of f of x, okay, if negative 5 is 0 of f of x, it means that f of negative 5 equals 0, right? This is the same as negative 5 is 0 of x. It means f of negative 5 equals 0. And f of negative 5 equals 0 based on factor theorem. Based on factor theorem, f of negative 5 equals 0, we can imply x minus 5 is a factor of p of x. You see that? Or in other way, we can x plus 5 is a factor of p of x. Right? Based on the factor theorem here. Because negative 5 is 0 of f of x, then f of negative 5 equals 0. And f of negative 5 equals 0 means x minus 5 is a factor. So I know that x plus 5 is a factor of this. If x plus 5 is a factor of this. Now, so that is just one of the factors. We need to factor completely this fx. Okay, I know x plus 5 is one of the factors, but we need to factor this completely. So we have to use syntactic division. Okay, right here c is negative 5. Okay, c is negative 5, so I set up the syntactic division. So I have negative 5, right? Then I do what? I write out all the coefficient down. 3, right? 25, right? 42, right? Negative 40, right? Then I drop 3 down, give you negative 15. So I give you 10, negative 50, give you what? Negative 8, 40, right? Add up and give you 0. Here you go. You see that? The remainder is 0. That's why I say f of negative 5 equals 0. Okay, so my quotient become what? My quotient is this, right? My question is this. So based on division algorithm, we can write our function as 3x to the third plus 25x squared plus 42x minus 40 equal to x plus 5, right? Uh, Divisor time quotient, right? So it's the quotient right here, right? So they start with the third power, you divide by the first power, then it give you the second power, so give you 3x squared plus 10x minus 8. Okay, so we successfully rewrite f of x as the product form, but we need to see is this it is a complete factor or not. You can see that 3x squared plus 10x minus 8 is another quadratic function, another trinomial, so we want to factor them. Okay, factor all the way out. So we have 3x here, we have x here. When we have 4 here and 2 here, right? And we want to have positive, right? So it means we have negative t and positive here. Here you go. So we successfully uh, um, factor f of x completely out. Okay, so that is part A. That is part A. Let's do part B. Okay, let me use part B. Let's do part B. So for part B, we want to solve it. Solving is easy. Solving is very easy, guys. Um, so I think I'm going to write over here because we don't need to have too much space. So in part B, we want to solve this polynomial, okay, for this function. And this function is right as this. So I just solved it because this is this, right? So I solved this one. Okay, so x plus 5. So x plus 5 times 3x minus 2 times um, x plus 4 is 0. Oh my god, this is too easy. It's just you just need applying a zero product property. So we have x plus 5 equals 0, 3x minus 2 equals 0, x plus 4 equals 0, and you get the x value of negative 5, it's actually 2 over 3, and x equal to negative 4. Okay, then it gives you the answer. So we have 3, 0, or 3 solution. Okay, 3 solution of a function. Okay, all right. Yeah, so in this lecture, I just talk about these two theorems, and we will continue with the new concept next time. So I want you guys, I want you to watch this lecture carefully, try understand the example. If you guys want me to go through something one more time, let me know. If you guys want me to do a couple more example similar to the example in this lecture, let me know also. Okay, and again, keep checking your email and your discussion board, your Canvas message to update the news information from me and from Valencia College. Okay, then I'll see you next time. Thank you so much.